Okay, so in Chem 30 right now, we are moving on with some ICE questions. This is questions that involve equilibrium, but instead of giving equilibrium, you're giving initial conditions. So there's three types of questions you can have when you're using the ICE chart. One is you use it to find information within the chart, and then you're able to solve for the K.C. constant. The other way is that you use the chart, and then you would have an unknown, and then you have the K.C. constant, and you use that information to find your unknown, which allows you to find the concentrations at equilibrium. And then the last one is some theory questions. So I have a couple examples here that goes through that, and this was from some homework that I had given my students. So the first one is you have some information about your gas being placed into a container, and then it gives some information at equilibrium about the hydrogen gas. So when you're setting this up, I just like to rewrite my equation and then set up my ICE chart right underneath it. So I.C.E. I is for your initial concentrations. So if we have the moles and we have the liters, we can divide it. So 0.75 divided by 1.50, and that will equal 0.5 moles per liter. Initially, they're not talking about hydrogen or bromine, so we can assume those are going to be 0. And then your change is based on the mole ratio. So because of this 2 in front of the HBr, we're going to take away 2x. We're subtracting because reactants get used up, and the 2 comes from the constant, and x is that change that we're trying to figure out. For your products, there's no number in front, so that would just be 1x, and we're going to add in because products will be formed. Then you add your columns together. So for E, it's going to be 0.5 minus 2x. For H, it's just x, and for Br, it's just x. This is the part we really care about because this is the part that uses the Kc, right? Kc is at equilibrium, and that's what we want to solve for. Now, this extra part about hydrogen being 0.13 at equilibrium, that means we can set our hydrogen value, which is just x, equal to 0.130. And now that you know x, you can plug it in for all of the x values, and now we would know all our concentrations at equilibrium. So now we can set up that Kc expression, which is going to be your hydrogen times your bromine divided by your HBr to the power of 2, right? Always products over reactants. And then we will fill in those values. So 1.30 times 0.130 divided by 0.5 minus 2x is 0.24, and that would all be squared. And then plug that into our calculator, and we would figure out that the Kc constant is going to be 0.293. And your equilibrium constant does not have any units, so that would be your answer for this first one. So setting up a very similar question, this time we again have, so this is written right here, I'll just write ICE right under it. We have some information about all 3 species, and we have that initial amount of moles, and then we're putting it into a 1 liter container. So if we divide each of those by 1, we'd have 4 for the CO2, 3 for the CO, and 3 for the oxygen. Then we can still set up that change by subtracting 2x, so that 2 is coming from the 2 out front, adding 2x, and then just adding x because there's no number in front. Now adding your columns, so you have 4 minus 2x, then we have 3 plus 2x, should go like this, and then the last one you have 3 plus x. So that is our information at equilibrium. Once again, we're going to figure out that Kc value, and it's telling us that at equilibrium you have 4.50 moles of oxygen. So the 3 plus x is your value of oxygen at equilibrium, and you can set it to the value that's given in the question. This allows us to solve for x, and that's going to be 1.5. Now that you know what x equals, again, you can plug it into all those x values, and then we can set up the Kc expression. So carbon monoxide squared times oxygen divided by carbon dioxide squared. So now that we have those values at equilibrium, we're going to go ahead and plug them in. So carbon dioxide, and I'm sorry, that's carbon monoxide, is going to be 6 squared. This part here was 4.5, and your denominator ends up being just 1 squared. So we can plug that all in into our calculator and we'll get 162. So that's our constant at equilibrium for this reaction. Now the next one we're going to do gets a little bit more messy, and this is instead of finding your K.C. constant, you're using your K.C. constant to find some missing information within. So we're still starting the same way. You're going to have your reaction and you're going to set up your ICE chart. So we have our reaction. If you set up your ICE chart, we have initially 0.3 moles of SO3 and NO are in a 2-liter container. So we want to take that moles and divide it by the liters, and you're going to get 0.15 moles per liter. So our initial concentrations. Again, we have no information about the products, so here we can assume they're 0. Then we can set up the change. Reactants are used up, so we'll subtract it. Products are formed, so you'll add it. Then for your information at equilibrium, you're going to just add your columns together, and then X and X. And this is the part that once again matters at equilibrium, because that's what goes into the Kc expression. So in this case, you have the Kc value. Your Kc equals 0.500 and one more 0. So we can now set this up, and you're going to have 0.5 equals products. So you'd have X times X, right, for both of these, divided by 0.15 minus X, and then that would also be times itself, since both of these equal the same. So products over reactants. So then what we can do at this point, realizing that X times X is just X squared, and the same thing at the bottom is squared, if we take the square root of both sides, then we would cancel out the squares. So we can, I'm just gonna come over here, have 0.5 will end up being X over 0.15 minus X. So at this point, we want to solve for X. So to do that, you have to get X out of the denominator. So we're going to multiply both sides by that binomial. Okay. Then we can distribute the radical through the binomial. So you would have the root of 0.5 times 0.15, and then you would subtract the root of 0.5 times X, and that will all equal X, because that X is still remaining. Now we want to isolate our number and move the X to the other side. So you'll add 0.5X to both sides. The root of 0.5X. And then we can collect like terms. So at this point, I'm going to put this in my calculator. The root of 0.5 times 0.15 is 0.106, and that number is going to keep going. I don't want to round too early. And on the other side, I'm going to have a value of 1 plus the root of 0.5, because I'm collecting like terms, and that will equal 1.707. Same thing, don't round too early, and that's your X. And we want to divide both sides by that number so that we can isolate X. And what you'll find out here, and I'm just going to come all the way to the top, is that X is going to equal 0.0621. So we've done all of that work, but then it's asking the equilibrium concentration for each gas. So going to your chart where equilibrium is, now that you know what X equals, you can plug it in for each of your X values to get the concentrations. So the concentration of your products, NO2, are the same as SO2, and that's going to equal the concentration of X, which is 0.0621 moles per liter. Then your reactants also have the same concentration. And if you plug that in, 0.15 minus that X value we solved for, you'll end up getting 0.08 0.79, and that once again is moles per liter. So I know this gets really messy, but those steps are always going to be the same. You want to set up your ice chart, plug it in, isolate X, and then go back to the equilibrium area, plug in X to get those gases. Now the last one is more of a theory question that can be asked. And in this one, we have our information and it's telling us the decrease. So they're giving us the change. So if I ignore I and E, essentially, I just want to look at the change. If I know that I'm still doing the same thing for my mole ratio, that I have minus 2x, and then oxygen would be minus x, and carbon dioxide would be plus 2x. If our oxygen, which is the middle one here, is going to decrease by 0.030 moles per liter, that is your X value. And that's all related. So if that's decreasing at the rate of 0.03, then carbon monoxide decreases twice as fast. So it's going to decrease at a rate of 2 times 0.03, which would equal 0.6. So because they're getting used up, it's decreasing. Whereas your carbon dioxide is going to produce at 2 times that rate. So you'd have 2 times 0.03. So that's going to increase at a rate of 0.6. So that's just more of a theory question based on the change value. Usually though, you'll see those first few examples more often. As always, I hope you found this helpful. If there's any other video I can ever do, just leave me a comment. Thanks for watching.